All right, chemists, today we're going to talk about calculating change in chemical reactions. So by that I'm talking about predicting how much of a product will get made with a certain amount of reactants, or we can calculate how much of the reactants will be consumed or do we need in order to produce a desired amount of product. And this is referred to as stoichiometry, right? Using those chemical equations to do calculations and make predictions in this way. To help us get started with this, we're going to take a look at an example from cooking. And this example is something you're going to probably say as we're going through, Mr. Sase, I can do this in my head. Why am I doing this? We're doing this way so that we can learn the process and apply it to our chemical reactions when numbers are not quite so simple and the ratios are not so easy. So let's take a look at making some pancakes. Now, when we have making our pancakes from a boxed mix, which may be blasphemy to some of you, but it's going to make our recipe here a little bit easier. I have 3 cups of mix. I'm going to put that with 2 cups of water, mix it all together. When I cook it, that's going to get me 18 pancakes according to the back of the box. Now, we know that's never true because I like my pancakes a little bit larger, but let's pretend that the back of the box is actually correct, and we're going to get 18 out of this. So I can model this recipe as a chemical reaction where I have 3 cups of mix plus 2 cups of water yields 18 pancakes, and those values there give us a ratio. Right? Just like in a chemical reaction where we had a ratio of the reactants to each other, the reactants to the products, I get a ratio of my ingredients to the amount of pancakes I'm going to get out of this. Right? Because a chemical equation is really just the recipe for making the products in that chemical reaction. So to take an example from this, let's say I'm not going to follow the recipe exactly as it's on the box. Let's say I want to use 6 cups of flour to make pancakes because pancakes are amazing and I want a whole bunch of them. And we could pretend that we're going to share them, but really they're just amazing. So we have 6 cups of flour. How many pancakes can I make? And you're all going to say, Mr. Sase, I could do this in my head. Stop, because it's just twice the recipe. But again, we're going to learn the tool here so that we can apply it to our chemical reactions in a moment. Okay. This tool that we're going to be using is something called a BCA table. It stands for before, change, and after. What this does is it helps us model what's happening at the initial state of the reaction, right before we do anything, what's going to be changing over the course of it, and then as a result, what do we have at the end of the reaction? How many pancakes do we have? Do we have any mix left over? Do we have any water left over, etc.? Right? So starting off with the example problem that we gave where we had 6 cups of flour, I know then that at the beginning of my reaction, I have 6 cups of flour. So I put that in the before part of the little table here with under my cups of mix. Now my water, I'm going to be getting that from the tap in the kitchen, which means that I have really as much water as I could possibly want because I could just turn the faucet on again, unless we're in a drought or the plumbing breaks or something like that. Like there's plenty of water available. So usually what we refer to that in a chemical reaction when there's more than enough of something is excess, meaning I can use it up for the reaction. It's not going to run out. At the end of it, I'm still going to have plenty of it left over. So this is similar to most cases when maybe we're burning something and we're getting oxygen from the atmosphere, because generally we're not going to be using up all of the oxygen in the atmosphere unless we're in some kind of sealed container or compartment. In these tables, sometimes excess is instead abbreviated as the letters XS. At the beginning of this cooking recipe, I have 0 pancakes, so in the before section, I'm going to put my 0 there. All right, so now we start to cook. I'm going to take my 6 cups of mix and I'm going to use all of it up. Right? So minus 6 cups in the change there. Now what's going to happen with the water? Well, from my recipe at the top here, I know that for every 3 cups of mix, I'm going to have 2 cups of water. Now you can all do this in your head, I'm sure. But again, I'm going to model this because I can use dimensional analysis and this ratio here to solve this problem. 6 cups of mix. Now I know that there's a 2 cups of water for every 3 cups of mix. And now the way that I set up my equation here, the cups of mix cancels out. So by solving this, I would know how many cups of water I'm going to use over the course of this reaction. And again, I know you can do this particular one in your head. We're showing the model that we're going to use throughout. Right, so 6 times 2 divided by 3 means that over the course of this, I'm going to need to use up 4 cups of water. And as a result, how many pancakes am I going to make? Well, I can use the 6 cups of mix or the 4 cups of water at this point, but again, I can use that ratio where 6 cups of mix times my ratio was 18 pancakes for every 3 cups of mix. Cups of mix cancels out. 6 times 18 divided by 3 gives me 36 pancakes. Okay, so now after, this is just a matter of simple math, we started with 6 cups of mix. We took away 6 cups of mix. So that means at the end, we're going to have no cups of mix left over. For the water before the reaction, quote unquote, we had an excess amount of water. We took away 4 cups. Afterwards, well, we still have excess. We still have as much as we want, right? We don't have a limit there. At the beginning of the cooking reaction, I had 0 pancakes. I made 36 over the course of the reaction, so at the end of this, I'm going to have 36 pancakes. Okay. So this is essentially how we can use a BCA table to help us predict what's going to be present at the end of the reaction in terms of the amount of reactants and the amount of products. All right, again, this was an easier example, but let's look at how we can apply this when things get a little bit more tricky. So let's say, for example, somebody, maybe me, maybe my fiance, maybe somebody else, maybe somebody drops the measuring cup, because this has actually been known to happen in my house here. And it broke. And now we can only measure things out in tablespoons. Now, because I still really want pancakes, I did take my little tablespoon and I measured out all the pancake mix that I have. And I still have 37 tablespoons of pancake mix. But my recipe is in cups. This is bringing back some of the work that we did earlier in the year, right, with dimensional analysis and unit conversions. We can still use our same BCA table, but now we're going to have a little bit of extra work in here, right? Again, prepping us for what's going to be coming with chemical reactions. Before I begin cooking, I have 37 tablespoons of my pancake mix here, but my cooking recipe is in cups, which means that when I try to use the ratio to figure out how much water I'm going to use and how many pancakes I'm going to be making, I need to have cups to do the ratio. So before I could do anything else, I'm going to need to take my 37 tablespoons and I'm going to need to figure out how many cups of mix I actually have here. Now, this value can be obtained from your conversion chart, but there are 16 tablespoons in every 1 cup, which means that right now at the start of this, I have 2.3 cups of mix. Now, again, I'm getting my water from the tap, so more than enough of it. I have excess, and I have 0 pancakes at the start. My change, well, I know I'm going to use up all of the mix. There's no way I'm going to leave any of that left over. So 2.3 cups is going to get consumed, which means that for my water, I'm going to need to take 2.3 cups of mix and figure out how much water is going to be consumed in the ratio, 2 cups of water for every 3 cups of mix. Tells me that I'm going to have to use up 1.53 cups of water. And again, using my ratio, if I have 2.3 cups of mix, and I get 18 pancakes for every 3 cups of mix, then as a result of this, I should get 13.8 pancakes. Now, that means I can have 13 and then one that's a little bit tinier, or we can have 12 and one that's really, really big. But we have 13.8 pancakes. So at the end of this, I'm going to have 0 mix left over. I'm going to still have a whole lot of water with 1.53 cups less, but that still just means a whole lot of water. And I'm going to have my 13.8 pancakes. All right, so here we had to do some conversions in order to get to the values we were able to use from the chemical equation, right? Because here in this ingredients, here in the recipe, we had cups as our value. We can't use the tablespoons directly the way they are. So how does this then turn into a chemical reaction, right? What's going on here? Let's take a look at the combustion of hydrogen gas to make some water. Right? We're going to take our recipe, right? The way we produce water, where we take our hydrogen gas or oxygen gas, we're going to make some water from it. We can represent that with a chemical equation as long as it's balanced. So here we have the chemical reaction where we're going to have two hydrogen molecules, one oxygen molecule, and together those would produce 2 units of water. So this particle model here represents what I have at the start of this reaction. Right? So again, I'm going to use this to try to transition us to how we apply the BCA table to this. But we know from this, I'm using these big white ones here as oxygens and the tinier ones as the hydrogens. We know that to make water, we need 2 hydrogens and 1 oxygen. So for example, using my particle model, I can pair them up such as this, where 2 hydrogens and 1 oxygen, 2 hydrogens and 1 oxygen, 2 hydrogens, 1 oxygen. And I'm going to keep doing this until I am unable to pair any further. Okay. At this point, I can't make any more waters because I've ran out of hydrogen gas. So at the end of this reaction, I should have 1, 2, 3, 4, 5, 6 molecules of water. And I'm going to have 3 units of oxygen gas left over because we did not have enough hydrogen in order to actually react them. So here we have an example where we don't have an excess of one of the reactants. We have a set amount, and one of them is going to run out first. And as soon as that one runs out, the reaction is going to have to stop. Right? We can't produce the maximum amount of water that the oxygen would indicate we would because we don't have enough hydrogen to actually do so. So this is what we refer to as hydrogen here being the limiting reactant. It's going to limit how much we can actually make because we run out of it. So if we take this and try to apply it to the BCA table, right, to represent what's happening, we started with 6 molecules of hydrogen and 6 molecules of water, and oxygen, and we had no waters at the start. But as this reaction was happening, we used up all 6 molecules of hydrogen. We only took away 3 molecules of oxygen, and we produced 6 molecules of water, right? Just by counting up the pictures on the diagram. So this means at the end of the reaction, I have no hydrogen left, right? Limiting reactant, as we just described. We're going to have 3 molecules left over. So here again, we have an excess. And we have 6 molecules of product actually made. All right, so that's well and good, but we often don't do reactions with just 1 molecule, 2 molecules, 6 molecules at a time. We do them with billions and trillions. Right? Remember, we often refer to that as the mole, right, when we had that really large number of molecules. So here we can see where we can represent the same idea, but with moles, right, where we have 1 mole is 6.02 times 10 to the 23rd molecules, right, a really large number of things. So just like in the previous example where I had 2 molecules of hydrogen for every 1 molecule of water, if we scaled that value up, we can say 6 moles of hydrogen for every 6 moles of oxygen at the start. We used up 6 moles of hydrogen gas, 3 moles of oxygen gas to get to what we had at the end of the reaction. Right, we're just scaling it up because a mole, remember, is just a word that represents a really large number of items, right? It's still a counting word, just like the numbers 1, 2, 3, 4, 5, and 6 would be. So, great. We understand how to use the BCA table. We know how to predict how much is going to be there when we can use these values in our chemical reactions, because the balanced coefficients in a chemical reaction tell us the mole ratio or the molecule ratio of the reactants to products. Except we can't count the atoms when we're doing a lab, when we're doing a reaction. So what do? We have to count by using mass. So remember when we had talked about mole conversions and calculating how many atoms were in a different objects way back when, we used molar masses to convert between masses of an object and how many atoms or moles of atoms are present in that object. So we need to bring back some of that knowledge, and here's how it gets applied. So from mole conversions, remember that we had two conversion factors that we were going to be using extensively. One was that 1 mole of any substance, here we're going to call it substance X, has a set number of things in it, whether that's a molecule or an atom. If it's an ionic compound, it's the number of formula units, right? It's 6.022 times 10 to the 23rd of these things. Now, for each different substance, right, that value is always going to be the same. It's always that number of things. However, since some molecules have more atoms than others, and not all atoms have the same mass, the mass of that 1 mole of things is not going to be the same for every substance, right? That mass is referred to as the molar mass. And we got that for elements by looking at the periodic table and rounding the atomic weight value to 2 decimal places. Recall from our project also that if we have a compound and we're trying to find the formula mass of a compound, we just add up all of the atoms that are in that compound to get the molar mass of the compound. So here as an example, we have 1 iron atom, we have 3 oxygens, we have 3 hydrogens. So to get the molar mass of iron 3 hydroxide in this case, this is the calculation that we would do, getting the sum of those molar masses. All right, great. So let's tie this into our example reaction with the hydrogen, similar to how we had to do the tablespoons conversions when we were talking about making the pancakes. This is an example of something that's commonly called a mass-to-mass stoichiometry, because we're trying to start with the mass of reactants and figure out mass of products. The term's not entirely important, but if you are looking for extra practice or reading online, prepping for AP, anything like that, this is a term you might see, mass to mass. So here we have 8.22 grams of hydrogen. We still have an excess of oxygen because I'm going to burn this hydrogen here in the atmosphere, right outdoors. It's going to get oxygen from the air. And we're going to be producing water. At the start of this, we have no water. We have a certain amount of hydrogen. We have excess oxygen. That's represented in my BCA table. And I want to figure out what's going to be produced. Now, I can't immediately use the ratio in the reaction because this ratio represents molecules and moles. It does not represent mass, right? Because we know a hydrogen atom is really, really tiny. It's the smallest element. Oxygen's not. So there's no way that those atoms would have the same mass as each other or even be remotely comparable, right? We need to convert this to the unit that's actually in the chemical equation, similar to how we converted the tablespoons in the pancake mix to cups, because that's the value that was in the ingredients, right? That was in the recipe. So first thing I need to do is take my mass of hydrogen here, and I need to convert it to moles to figure out what I'm actually dealing with. And since H2 is the formula mass of this is going to be 2.02 grams, because that's the mass of 2 hydrogen atoms. Which means that for this, I'm starting with 4.07 moles of hydrogen. Okay, so because I have excess oxygen, I know I'm going to use up all of this hydrogen. And I want to know, well, how much oxygen am I going to produce? Well, I'm going to be taking away 4.07 moles of hydrogen. Again, using my dimensional analysis, I know that there's 1 mole of oxygen for every 2 moles of hydrogen. Again, I got these values here from the ratio up in the reaction. So from that, I know I'm going to be using up 2.04, right, rounded for sig figs, moles of oxygen. And doing something similar again for the products, I'm going to be producing, so there's the plus sign, and using my conversion, I have 4.07 moles of hydrogen. And here from the chemical reaction, we see that there's 2 moles of water produced from every 2 moles of hydrogen, which means 4.07 times 2 divided by 2 is 4.07 are going to be produced. So at the end of this reaction, I started with 4.07 moles of hydrogen. I used up 4.07 moles of hydrogen. I have 0 remaining. I had an excess amount of oxygen. I used up some of it. I still have an excess amount of hydrogen of oxygen. And then at the end, I had 0 grams of water at the start. And now I produced 4.07 moles, but I need to know what that is in grams. So 4.07 moles of water, and I'm going to convert that back to grams using the molar mass of water now. So we get that by getting 2 hydrogens and 1 oxygen, right? Adding up those masses. That is 18.02 grams for every 1 mole of water. So when we multiply that through, this reaction produces 73.34 grams of water. Right. So if we apply the same process we did to the pancake recipe, we can use similar steps to figure out how much of the product is going to be made in this reaction here based on how much of the reactant we're using in the reaction. Another way that this is sometimes approached with very similar steps is, instead of having masses, what if we had just the number of things, right? A number of molecules, number of atoms, formula units, etc. This just means that we would do pretty much the same steps as before, but instead of converting from mass to moles, we're going to need to convert our molecules over in order to do this, right? So we're always going to want to get to moles first, because that's generally the value, that is the value of the ratio here at the top. So 9.3 times 10 to the 23rd molecules, convert that to moles. And we do that using the other conversion factor, that 1 mole of a substance always has 6.022 times 10 to the 23rd things, in this case molecules. So based on that value, at the start I have 1.54 moles of H2. And in my change, I have excess oxygen again, so I'm going to use up all of this. So at the end of this reaction, I should have none left over. For the oxygen, I can again calculate my ratio of what's going to be used up, but because we have excess, we know that at the end of this, we're still going to have some left over, so we could realistically skip that step for now. But for my water, how much is being produced? Well, I have 1.54 moles of hydrogen. I know from my chemical equation that 2 moles of water is produced for every 2 moles of hydrogen gas consumed, which tells me that I'm going to be producing 1.54 moles of water. And 1.54 moles of water, as we already figured out from back in the hydrogen, is the equivalent to 9.3 times 10 to the 23rd molecules. Right, so here we could see it's not entirely necessary to go to moles when we already have the number of things, because the reaction, remember when we were first doing them with the particle model, we use the number of molecules in that case. But whenever we're using the mass, right, because that's not comparable between 2 different compounds or elements or molecules, we need to always get to something that is, right? We need to get to the number of moles first. All right, so what happens though if one of our reactants is not in excess? What if we have a set amount of both of the reactants, and then we have the situation where one of them is going to run out, and then therefore it's going to stop our reaction? Looking at this offhand, it looks like I have a lot more oxygen, but I also know that oxygen is just a bigger atom. So do I really have more of it, or is it just weighing more? So we need to convert these values into moles and take a look at our ratio to figure out which one is going to be in excess, which one's going to run out first, what's going to be controlling the reaction, etc. So first thing I'm going to do is convert both of these mass values to moles using their molar masses. So for hydrogen, the molar mass, as we've been using, is 2.02 grams. That's the mass of 2 hydrogen atoms. For oxygen, 50.25 converted to moles. The molar mass for O2, which is the mass of 2 oxygens, is 32 grams. Right, so by solving each of these, I find that for my hydrogen, I have 3.22 moles to start, and for my oxygen, I have 1.57 moles to start. Okay, well, how do we figure out which one runs out first? We need to compare the two reactants to each other using the mole ratio. Basically, pick one of those values to start with and figure out, based on that, how much of the other one would be required to complete the reaction. So that sounds a little confusing, so let's take a look at my example. I'm starting with the moles of hydrogen, right? It doesn't matter which one you pick. But I'm saying that if I'm going to use up every single bit of this hydrogen gas, how much oxygen would be required? Right? I can figure that out using the mole ratio. Right? It's a 1-to-2 ratio. That for 3.22 moles of hydrogen, I would need 1.61 moles of oxygen. And I forgot to write out the whole word mole. Okay, now we can compare. This is how much oxygen is required, and this is how much I have available. Clearly, I do not have enough oxygen. I'm going to run out of that in this case. And what that means is that since I'm going to run out of oxygen before I run out of my hydrogen is actually going to be my excess reactant here. Now, it's not going to be an unlimited amount left over, like we can figure out exactly how much is left, but my oxygen is going to be my limiting reactant, right? It's what's going to control the reaction, because as soon as I run out of oxygen, the reaction is going to stop. So in order to figure out the change, I need to use the limiting reactant. Right? I'm going to use up all of the limiting reactant, and meaning I'm going to have none of it left over. To figure out the change of the other two now, I need to use and base everything on that limiting reactant value. Right? So if I had 1.57 moles of oxygen being used up, how much of the hydrogen did that take with it? Did that consume? Well, 2 moles of H2 for every 1 mole of O2 tells me that when these react, I'm going to need to use up 3.14 moles of hydrogen. So if I started with 3.22 moles of hydrogen and I used up 3.14 moles of hydrogen, right, simple math tells me that at the end of this, I'm going to have 0.08 moles of H2 left over. I can figure that out, or figure out what that is in grams if I would like, by converting that using its molar mass. And what that means is that at the end of this, I'm going to have 0.16 grams of hydrogen left over, right, remaining. For our products, right, that's being produced and being controlled by the oxygen getting used up. So I'm using up 1.57 moles of oxygen, which means I'm going to be producing, right, plus 2-to-1 ratio, 2 moles of water for every 1 mole of O2. Tells me 3.14 moles of water will be produced. But since we're looking for grams, I'm going to take my 3.14 moles of water. I'm going to multiply it by its molar mass to convert it to grams, which tells me that from this reaction, I'm going to get 56.6 grams of water produced. So to sum up what we've been talking about, right, stoichiometry, it's a way to use the set ratios of reactants to products, right, or ingredients to the thing you're making, to predict how much of the reactants are going to be consumed, what would be left over, and how much of the product is going to be made. Right? And this is essentially the whole foundation of chemistry and applying chemical reactions in industry and business and labs, because there's usually a desired product that you want, and knowing exactly how much of the different reactants will get you that product will allow you to maximize profits and resources so that you're not wasting stuff, you're not ordering too much or too little, etc. But to do all of this, you need to have the mole ratios. Right? You need to have a balanced chemical equation, and you need to convert everything to the moles first. Let's take a look at two more examples, right? Just putting everything all together. Here's a word equation where this is the way we would typically see something, typically see a problem written out, where we have, in this case, aluminum metal reacting with copper 2 chloride. Now, notice here, it doesn't even tell you what the products are. So first thing you need to do is figure out what type of reaction it is and what's going to happen. Well, I have aluminum metal. I'm reacting that with copper 2 chloride. Right, so this is where writing our names and formulas comes into play. So from this, I should recognize that I have a free element and I have an ionic compound. This is the signature of a single replacement reaction. We know that this reaction would occur because aluminum is higher than copper on the activity series. Right? This is also similar to the reaction that was demonstrated in one of the previous videos. And what this means is that after this reaction, we're going to have aluminum chloride being produced along with copper metal. We can't yet do the BCA table and do all of the calculations because this reaction is not balanced. So I'm going to need to finish that out. All right, we have a 2-to-3, 2-to-3 ratio for the reactants to the products. From the information given to us in the problem, I know that I have 54.40 grams of aluminum, and I have 269.70 grams of copper chloride at the start, and I have not done the reaction yet, so I have 0 of the other two. Now, again, we see that there's nothing in excess, so we need to figure out which one's going to get used up first. Right, check for the required amounts. First thing I'm going to do is convert both of these to moles. So I'm going to take the aluminum first, and I'm going to use its molar mass from the periodic table, 26.98 grams per mole. And I'm going to use that to solve for moles, 2.027 moles initially. For our copper chloride, 269.70 grams, using its molar mass, which is the mass of 1 copper and 2 chlorines all added together. That's 134.45 grams, which tells me I'm initially having 2.0060 moles. Now, quickly looking at this, right, we're going to do the math in a second, but quickly looking at this, we see that we have, let's say, approximately 2 moles of each of these substances at the start. And in my reaction, I see that there's a 2-to-3 ratio. And I should be able to really quickly see that I'm not going to have enough copper chloride because I don't have that 2-to-3 ratio. Right? It's really apparent here because both of them are 2-point-something moles initially. So I'm going to go ahead and just do the math to demonstrate that. But as you're doing these on your own or practicing, you should be able to readily see and prove, right, that there's not going to be enough. 2.027 moles of aluminum. We can figure out how much copper chloride that would require. So based on this ratio, in order to use up all of the aluminum, I would need 3.01 moles, 0.14 of copper chloride. And clearly that is not happening here. So what that tells me is that I'm going to run out of copper chloride in this reaction. I'm going to have excess aluminum at the end. All right, so I'm just making a note of those down here. And so over the course of the reaction, I'm going to use up all of my copper chloride. Right, there's going to be none of that left over. And for my aluminum, I'm going to take the copper chloride's initial value, and I'm going to figure out how much aluminum is it going to consume. Right, so 2 moles of aluminum for every 3 moles of copper chloride tells me that over the course of this reaction, I'm going to use up 1.3373 moles of aluminum. So if I started with 2.027 moles of aluminum and I'm using up that amount, at the end of this reaction, I'm going to have 0.690 moles of aluminum remaining. And again, using that molar mass, I can convert using the mass of aluminum, and that comes out to 18.6 grams of aluminum will be left over out of the initial 54.4 grams. To figure out my 2 products, I would do the similar steps as the other ones, using my limiting reactants value, 2.0060 moles of copper chloride, and for the aluminum chloride, that's a 2-to-3 ratio. Tells me that here I'm going to produce 1.3373 moles of aluminum chloride. And if I do the same thing, but it's a 3-to-3 ratio over here, I would produce 2.0060 moles of copper. Taking each of those and converting them to grams using their formula masses. We've been doing a bunch of those, so I'm not going to show the steps directly here, but we would take 1.3373, and the molar mass of aluminum chloride would tell us that this would produce 178.30 grams. And for the copper, we would produce 127.48 grams. Here's the one last example where we're trying to produce a certain amount of product. In this case, the question asks us how much of each reactant would be needed to synthesize 25 grams of iron 3 oxide. And it tells us that we're synthesizing, so we should be able to infer from that that we're combining multiple reactants to form the iron 3 oxide. In this case, we're combining the different component elements. So iron 3 oxide is our product, and its component elements would be iron metal and oxygen gas. Balancing out the equation, we have 2 iron 3 oxides for every 3 oxygen gases and 4 iron metals. That's a 4:3:2 ratio. Now, it tells us that we're going to be synthesizing 25 grams of iron 3 oxide, so that's how much we're trying to produce at the end of this reaction. Initially, we have 0. So essentially, we need to work backwards here because we're trying to figure out how much of each thing do we have at the start of this reaction. So following similar steps that we did last time, we need to use the mole ratio to find the relationship between the products and the reactants. So to do that, I'm going to need to take my 25 grams of iron 3 oxide and convert that to moles using the molar mass of iron 3 oxide. Now, the molar mass of iron 3 oxide, right, 2 irons and 3 oxygens, gives us a value of 159.70 grams. So here we are producing 1.1565 moles of iron 3 oxide. So if we were producing that much, we want to figure out, well, how much of each of the other reactants were we using up? So if we produced this much, we were taking away 0.1565 moles of iron 3 oxide and using the mole ratio to figure out how much oxygen gas was needed to do that. 3 moles of O2 are required for every 2 moles of iron 3 oxide, which tells us that we must have consumed 0.2348 moles of O2. And for our iron metal, we must have consumed 0.1565 moles of iron 3 oxide times the mole ratio, 4 moles of iron for every 2 moles of iron 3 oxide. Tells me that for my iron, I must have consumed 0.3130 moles of iron. To figure out what those are in terms of masses, I would just need to convert the mole values now back to mass. So 0.3130 moles of iron times the molar mass of iron is 55.85 grams per mole. And for oxygen, 0.2348 times the molar mass of oxygen tells me that for my iron, I initially needed to use up 17.48 grams. And for my oxygen gas, I must have used up 7.514 grams of that. And here's a quick check to see if we had approximately the right values. Granted, there is some sig fig rounding in here. We know from the law of conservation of matter that matter cannot be created or destroyed. So if I'm going to produce 25 grams of product, I must have begun with 25 grams total of the reactants. And if we add those two together, we do get approximately 25 grams, the difference in with the sig fig rounding, of course.